Hello guys, welcome back to my YouTube channel. Today in this video we'll learn about the subject of VLSI, very large scale integration design, which is the most important subject in ANC engineering. In this video we'll learn about explores the fundamentals of low power VLSI design and focusing on techniques and strategies to minimize power consumption in integrated circuits. Now let's move on to the introduction to VLSI design. What is VLSI? Very large-scale integration refers to the design and fabrication of integrated circuits containing millions or billions of transistors on a single chip. Mounting of millions and billions of transistors on a single chip is called as VLSI. And VLSI applications are VLSI circuits power a wide range of devices from smartphones and computers to medical equipment and aerospace systems, where we use the microprocessor chips where the microprocessor chips, thousands and billions of the transistors are mounted, which the chips are used for smartphones, computer, and also to the medical equipment, and also to the aerospace systems. Now let's see how the power consumption in VLSI circuits happens. The first is leakage current. Current flowing through inactive transistor due to imperfection in fabrication. And the second is switching activity. Power consumed during transitions between logic states 0 and 1. Now let's see the first type of power consumption in VLSI. The first one is static power consumption. In static power consumptions, there are three types of leakage where there are threshold leakage, gate leakage, and junction leakage. Now let's see what's the meaning of these three one by one. The first one is sub-threshold leakage. Leakage current in MOSFETs when the gate to source voltage is below the threshold voltage. And the second one is gate voltage. Gate leakage. Current flowing through the gate oxide layer influenced by gate voltage and oxide thickness. And the third leakage in the static power consumption is current leakage across the PN junction of a diode, primarily due to reverse bias. Let's move on to the second type of power consumption, that is dynamic power consumption. In dynamic power consumption, we have two types, capacitive loading and switching frequency. Now let's see what is the meaning of capacitive loading. Energy required to charge and discharge parasitic capacitance in the circuit. Capacitive loading is nothing but in VLSI, the capacitance on the chips need to be charged and discharged. When this process takes place, the power consumption will be high. So this will be considered as the dynamic power consumption. And the second one is switching frequency. Higher switching frequency lead to increased dynamic power consumption. In VLSI, the chips need to acquire the frequency when the chip is switching from one frequency to the higher frequency, like lower to the higher frequency, it consumes more power consumption. Hence, it will be considered as a dynamic power consumption. Let's see how can we reduce the power consumptions either in a static way or in a dynamic way. Now let's see techniques for low power design. The first one is voltage scaling, and third is clock gating. Second one is power gating. Let's see what is voltage scaling. Reduce operating voltage to minimize power consumption. In VLSI, the chips need to be operated in a low voltage. If it works in a low voltage, then surely we can make the chip as a less power consumption chip. And the second one is clock gating, disabling clock signals to inactive circuit portions, reducing switching activity. Clock gating is nothing but if the chip wants to work, if the clock signals are continuously giving impulse, then the chip consumes more power. So by disabling or deleting the clock signals, we can consume more power. Hence, this is also can be considered as the techniques for low power consumption. And the third is power gating, disabling entire sections of the circuit when not in use, eliminating static leakage power. Power gating is nothing but like if the work is done with the circuit, then it should be entirely disabled by current flowing or any usage. Then by eliminating it, we can consume more power consumption and we can consume static leakage power too. If the chip is not working or if the circuit is not working, if the current will be flowing, there will be a leakage power. Hence, we can reduce the static leakage power by using of power gating. Now let's come to the gate level optimization. There are three steps. The first one is logic minimization, gate sizing, buffer insertion. Let's see one by one what is the meaning of how the gate level optimization is done. The first one is logic minimization, simplifying Boolean expression to reduce gate count and switching activity. By using Boolean expression to reduce gate counts, if the gate counts is continuously counting by the using Boolean expressions, then the power consumptions will be more. So by reducing the gate counts, we can gate level optimization can be done. The second one is gate sizing, adjusting gate sizes to optimize performance and minimize power consumption. As we say, VLSI works on making the chips into the smaller size and giving the performance in the higher, giving the performance in the higher and making the minimize power consumption. The VLSI is right now working for that. Now let's gate sizing, adjusting gate sizes to optimize performance and minimize power consumption. Gate sizing is nothing but like minimizing the gate sizes, like instead of implementing the complex gate sizes, we can implement the easier gate sizes which is smaller to understand and even readable, which is minimize power consumption. Next is buffer insertion, adding buffers to reduce signal delays and minimize power dissipation. If we use buffers like non gates, there will be a reduced signal delays. The delays will be eliminated or minimized and minimize power dissipation. Now let's see circuit level optimization. There will be three layers like parallel paths, pipelining, low power adders. The first one is breaking tasks into parallel subtasks to improve throughput and reduce power consumption. Pipelining, dividing a complex circuit into stages to allow for concurrent processing and reduced power dissipation. Low power adders, utilizing specialized adder designed to minimize the power consumptions while maintaining accuracy. Now let's see system level optimization. There are power aware scheduling, data compression, low power communication protocols. Let's see one by one. Power aware scheduling, optimizing task scheduling algorithms to minimize power consumption across the entire system. Data compression, reducing data volume to minimize power consumption in communication and storage. Low power communication protocols, utilizing energy efficient protocols for data communication between system components. Now let's come to the conclusion of this video. Case studies and conclusions are like the case studies are 20% power reduction. After following all these techniques and methodologies, we can reduce power reduction by 20%. Case studies demonstrate significant power savings through various low power design techniques. And we can get the battery life extend for 50% by following all the steps in this video where I have teached. Increased battery life and enhanced device performance are crucial benefits. Thank you.